Hopefully it's not too large here because we're going to be doing a couple arc marks here. There we go, right through angle C. Everyone's got 2 points of intersection, correct? Let's put your compass point on one of those points of intersection for me. You can open or close or keep it the same, but these next 2 arc marks you make need to have the same opening on your compass. And what you're going to do, you're going to make another arc ahead of that one. I'll make it red. And then you're going to come over to the other point of intersection and make a second arc mark. So those two intersect each other. Line up your straight edge with vertex C when you're ready. And construct your first angle bisector. Everyone's good? All right, let's move to angle B now. Let's move to angle B. Take your compass, put it on vertex B. Make sure you start keeping track of your arc marks here, because some of you guys make them so large that they all of a sudden intersect previous angles. Same thing, make an arc, one arc through angle B. And then from those 2 points of intersection, 2 more arc marks out ahead of the first. And make your second angle bisector when you guys are ready. So we should have 2 until we make them a little longer. Okay, so I want you to see how they intersect. It looks like we got 1 more to go. Looking good so far. All right, let's go up to A. And let's see if some magic happens here. And I know compasses shake a little. But I'm hoping that all 3 of your angle bisectors intersect at the same point. Or at least you have like maybe a tiny, tiny triangle as a space opening. It should be a huge triangle, but it should be right around where the points of intersection are. I like how some of you guys make the huge, huge dot to cover up your huge triangle. I do it too. I laugh because I do it when I mess up. All right, so what did we just figure out here? In a triangle. Conclusion, in a triangle. What did we just construct here? 12, what did we just construct? The angle bisectors are, I do not want to keep saying intersect at a point, intersect at a point, intersect at a point. I don't want to keep saying that. I want to use the vocab. The angle bisectors are 13. What do I say with intersect at a point? 13? Concurrent. Perfect. They are concurrent. Where are they concurrent? At this point that I got a new name for. We had circumcenter on Thursday, where the angle bisectors meet. In center. In center. Questions? All right, so now you know how they're formed by the angle bisectors in center. Special fact time. Special fact about the in center. And I'll write it right underneath this diagram. The fact, in center is equidistant from the sides. Not the vertices. That was the circumcenter on Thursday. Not the vertices, but from the sides of the triangle. Go back up to the diagram right above it, right here. I will let you know, ready? D is the in center. D is the in center. Can somebody give me 3 line segments then that are congruent to each other? If D is the in center. 3 line segments now that are congruent in that diagram. If D is the in center, equidistant from the sides. Nick, let's roll. D, what was the first one? I couldn't hear you, sorry. Yep, congruent to? Congruent to? Got it. Also, for a little bonus, there are multiple answers to this next question. Multiple answers. If D is the in center, can someone just name one pair of angles that are congruent up here? Name a pair of angles that are congruent. There's multiple answers up here. Multiple. Just not one I'm looking for. There's multiple, but I only want to write one. D is the in center. It was formed by the angle bisectors. D is an in center. It was formed by the angle bisectors. Will, what do you have?
DBF and DBE.
DBF congruent to DBE. That's a good pair. Again, how does Will know that? Because this BD is an angle bisector. It's formed with the in center. You could also give me 2 more pairs around that triangle as well. Questions on the in center? Okay, pencils, pens down. Here we go. Anytime I can, I'm going to try to quick quiz you here. This is nowhere to be found. We already have 2 sets of lines that are concurrent in a triangle. 2 sets. Please name one set for me before I move on. One set of lines that are concurrent in a triangle. 12. Remember, think of it. When I'm asking this question, I'm asking for these 3 lines intersect in a point. Okay, let's start there. The perpendicular bisectors are concurrent Here's where our mindset goes. Okay, yep, I got the perpendicular bisectors. That point's called the 20 circumcenter. So where those three intersect is called the circumcenter, and I should know what about that circumcenter so I can do this problem. 21?
The perpendicular bisectors
We got work to do, Dan. We got work to do. 28, what should I know about the circumcenter?
It's equidistant from the angles.
I know what you're talking about, Tyler. Equidistant from, I'm going to say vertices, though. Yep, but we're talking the same thing. All good. That's what I got to know. Those facts right there. And then now I just introduced a new set of lines, which are the what of the triangle. 28 again. Actually, you know what? You're good, Tyler. You've answered enough. 27, the what are all equidistant. Sorry, the all what are concurrent. I know the perpendicular bisectors are. We just spent 5 minutes constructing what? Who's got 27? Not here? Okay. How about 1? The angle bisectors are concurrent at a point called 22. In center. And the greatness about the in center, what's so good about it? 20.
They're equidistant from these sides.
I got 2 more left. 2 more of these. Okay, 1 coming up before you leave and 1 tomorrow. Figure out something. All right, I'm not yelling, I'm not mad, I'm just saying figure out something. Okay, because we need to keep these straight to even have a shot at any of these algebra problems. Anything you want to ask up here before I get to the third one? All right, before I get to the third one, I know this is breaking news, I'm going to have to give you a new vocabulary term. That's the same slide coming up. Yeah, very good. All right, so before I show you the third point of concurrency, let's talk about this new vocabulary term, altitude. Your teachers in the past probably have not used that term at all. I'm the first one to use it. Instead, what they've usually probably used is this term, height. All right, the height of a triangle is known as the altitude. We are going to use the word altitude in here. So here's an altitude. It's a segment. It is a segment in a triangle. It starts at a vertex. It has to start at a vertex. And it's drawn to the opposite side, so it's perpendicular to the opposite side. Let me say that again. Every altitude starts at a vertex and will be drawn perpendicular to the opposite side. Can you add any markings to your diagram right now then, if you know that? If we just went over that AD is an altitude and it starts at a vertex and is perpendicular to the opposite side, what markings are you putting on your diagram right now? 16, what markings are you putting on? Where? Let's name it. Name it. 3 letters. Name an angle. And anything else? Okay, so that's what we can conclude here. Angle ADB and angle ADC are right angles. Did I mention the word bisects at all? Good. So don't put it in your vocab either. All altitudes do form right angles. Bonus question. In a single triangle, how many altitudes exist? And the answer is not infinite. Sorry. I got one right there. In a single triangle, look at the definition again. In a single triangle, how many altitudes can only exist? What do you got, Brody?
3.
3, because there's only
3 vertices.
3 vertices. 3 vertices, right? So I got this one. Don't draw it in, but I'm going to have that one. And I'm going to have that one. And shocker, guess what's going to happen to all 3 altitudes? They'll all, thank you for using the vocab, they'll all be concurrent. Yes. Yes. We'll get to that in a second. First thing I want to do is let's construct an altitude so you know what one really looks like. I made a little note for me to here to remind myself. Anybody, what type of triangle is ABC? based on its angles, not it. Don't tell me scalene, isosceles, equilateral. Based on the angles, what type of triangle does this look like? Obtuse, yeah. This angle B looks a little bit bigger than a right angle. Yep, obtuse. So here's what I want. From vertex A, let's do an altitude. From vertex A. All right, so I know he told me it's got to be perpendicular to the opposite side. You think that's going to be my altitude? Think that's going to be it? Absolutely not. Why not?
Not perpendicular.
There's no way that forms a 90-degree angle. All right. You think that's going to be it? Think that's going to form a right angle from A? No. How about that? You think that's going to form a right angle? What am I trying to get at here? I don't care how many of these I draw in, they're never going to be perpendicular. My altitude's not going to be where? In the triangle. Guess where it's going to be? Somewhere outside. All right. So how do I do this altitude? You know how to do it already. You already know. We did a construction many constructions in the past where I would say, draw me a line perpendicular to this one, but going through P. What would you do with your compass? Anybody remember?
Like a smile.
Yeah, put your compass on P and do one of those bad boys, right? Well, look at what I've given you. Here's your point, and here's your line. So I'm going to put my compass point on A and try to make that smile face that John just referenced, but I'm going to have a problem, aren't I? I can only open up my compass so it intersects A, B in one spot. There's never going to be an opening I can make it so it intersects twice. Advice for me? Extend side BC. Good advice. Going to take my straight edge, extend side BC. Now I'll be able to get it to intersect in two spots. And then go to each point of intersection, right? Each point of intersection on extended side BC. Two more arc marks that intersect. And remember, an altitude comes from a vertex. So I'm going to line up vertex A with my point of intersection. And you're going to see the altitude being formed on the outside. You can draw it right through if you want. You can stop at extended side BC. Your call. It doesn't matter if you're drawing in an altitude. Should we put right angles there, right? Because it forms a right angle. So when I have an obtuse triangle, at least, might be more, but at least one of those altitudes will be on the outside. All right. Looking good. All right. I don't have the time here today, or I'm sure you don't have the patience either to do two more altitudes coming from C and A. So we're just going to write our conclusion here if we did end up doing that. This is kind of familiar. In a triangle, what did we just construct? The altitudes are concurrent. Yep, they would all meet in the same spot. Are concurrent. Oh, I'm not done yet. Because then what do I still have to tell you? What do we still have to know? What's that new point called, right? Where all the altitudes intersect? Point of concurrency is called. Not too sure if I'm spelling it right, but I don't care. Ready for this name? What'd you have already? Circumcenter, and then what else today? Incenter. Now you have the orthocenter. Orthocenter. Still got to tell you what, I'm not ready to move on. We know the altitudes are concurrent. We know the name of that point now, and now I got to tell you what. What's so special about it, right? The fact. Here's the only piece of good news today. It's not special. There is no fact. It's not equidistant from this. Nothing. It's just there. Just there. But, there's a but in honors geometry. You still have to know where it's located based on the triangle I give you. Okay? You've got to know where it's located. There's nothing special about it, but you should know where it is. All right, so there's 3 types of triangles based on angles. Angles. Name a triangle based on its angles. We just went over the obtuse triangle. So let's talk. If the triangle is obtuse, where is the orthocenter going to be located? Well, let's think. Well, can we think about this? Where's one of the altitudes always? Outside. So you knew when you drew in this altitude, when we drew in this altitude, the orthocenter has to be somewhere on this, right? Has to be. So where's your orthocenter for any obtuse triangle? Has to be located outside the triangle. Yep. I know it's got to be located somewhere on the outside. Another type of triangle. Well, based on angles.
Right.
Okay, we'll get right's a beast. We'll do that last. The one in the middle, acute. Yep. So if I have an acute triangle, what do you think about all the altitudes? Is there any shot one of them ends up outside? No shot. So that means the orthocenter is always located where? Inside. Yep, somewhere inside. Buckle up for this one. And then, yes, we have a, what's the deal with the right triangle? All right, I got to blow this up here. Just so we're clear. All right, there's my right triangle. Review. What's an altitude again? Starts at a? Vertex and is what to the opposite side? Okay, perpendicular. Starts at a vertex, perpendicular to the opposite side. Let's start with this vertex. You see the altitude? It's not going to be that, right? That's not perpendicular. It's not going to be that. That's not perpendicular. Do you see where it is? It's one of the sides, isn't it? That right there is an altitude. It's an actual side. So there is an altitude. Anybody remember what we call that in the right triangle? Leg. Yep. So there's one. Let's find a second altitude. Starts at a vertice, perpendicular to the opposite side. Where's the second altitude going to be? Not here. That's not where's the only time I can draw that'll be perpendicular? The other leg. Yep, here you go. So in a right triangle, 2 altitudes are the 2 legs. Can you see where the orthocenter is? The orthocenter is where the altitudes meet. Where do those 2 legs meet? There's your orthocenter. There's your orthocenter. It's where the 2 legs meet. In a right triangle, the orthocenter is where the 2 legs meet. Everyone see that? Because those are 2 altitudes. Wherever they meet is my orthocenter. So you just need to know where they're located. Questions? Oh, we are not done. Whew, here we go. Let's do this. First person I'm going to call on has the most power. They can yell out whatever vocabulary term they want. Let's try to make it to Unit 5 here. Okay? You can yell out whatever vocabulary one you want. I'll put it in the correct box, and then from there I'll ask questions. All right? So fill in any one of these right now. 23, your call. Fill in any one of these. Okay. Here we go. 28, what's its point of concurrency?
Circumcenter.
6, the fact about it.
It's equidistant from vertices.
It's like some of you guys filling in the big triangle. Equidistant from the vertices. Good. We're all good there. 23, give me another vocabulary term.
Angle bisector.
20, no, we're going to keep going around. All right, I'm good. 23, point of concurrency.
The incenter.
21, fact.
Incent with the sides are equidistant.
12, I gave you orthocenter.
The altitudes.
The altitudes, thank you. And I'm not going to go through this just to extend it, but we should know acute, right, obtuse, where the orthocenter is. Okay? This is exhausting. And you have one more coming tomorrow. Okay, one more box and column. 3 more boxes tomorrow. Questions? Before I let you go, here is the first problem tonight. P is the incenter. And number 27, I'm asking for the length of PB. And everyone see the hint I drew at the bottom of your page? What's the hint? What do I mean, use Pythagorean theorem? A squared B squared equals C squared, but it has to be on a right triangle. Do you see a right triangle in this diagram that contains PB, or you could use Pythagorean theorem? All right, I just want to make sure you get started on the right foot. Go ahead, let's get going. Grab some books.